Welcome, everybody. This is Dr. Andrei Holtz, and today we're discussing one of the most important topics in modern AI, responsible machine learning. In this session, we will explore how to design machine learning systems that are ethical, stable, and accountable. Responsible machine learning isn't just a set of principles, it's about creating systems that are fair, transparent, and effective in real world applications. We will cover frameworks, tools, and actionable strategies to help you build responsible systems. So let us begin. A responsible machine learning matters because it protects users, aligns with regulations, and builds trust in AI systems. It is also aligned with explainable machine learning. Also, the AI trolley problem on the right highlights the importance of accountability. When AI makes decisions, responsibility must be clearly defined. This lecture will guide us through the principles and practices to achieve responsible machine learning. Here is our roadmap for today. We will start with why responsible machine learning is critical and discuss the challenges it aims to address. Next, we will review global frameworks and technical strategies, including stability, fairness, and interpretability. We will conclude with tools, advanced methods like causal inference, and practical steps to implement responsible machine learning in your projects. Let us discuss why responsible machine learning is not just a technical requirement, but an ethical and societal necessity. First, responsible ML ensures fairness, transparency, reliability, and accountability. These principles are crucial for creating systems that people can trust. When we design AI that is fair and transparent, we show our commitment to ethical technology. Second, it helps us build trust with users and stakeholders. AI is increasingly integrated into critical decision making processes. Think about hiring, lending, or even judicial sentencing. If people affected by these systems cannot trust them, adoption fails and harm increases. Third, it ensures alignment with social and legal expectations. As regulations like GDPR and ethical standards evolve globally, ensuring our models meet these expectations will keep them relevant and safe. Finally, let us reflect on the consequences of neglecting responsible practices. The COMPAS algorithm used in criminal justice showed biases, with studies highlighting its unfairness in predicting recidivism. Similarly, mortgage approval algorithms were found to disproportionately reject some applicants, as reported in one of the reports by the markup. And these examples remind us of the real world harm caused by unaccountable AI. We must understand the weight of our responsibility as ML designers and practitioners. And these are not abstract failures, they impact real lives. And responsible machine learning is about using the tools and skills not to just innovate, but to innovate ethically and try to reduce potential harm. So, machine learning, while powerful, has its pitfalls. Bias may be introduced from historical data or sampling errors, leading to unjust outcomes. Many advanced models operate as black boxes, leaving us in the dark about how decisions are made. Instability becomes an issue when a model's performance degrades in the face of data drift, unexpected changes that occur in real world environments. And finally, vulnerabilities such as adversarial attacks can manipulate models with perturbations. Recognizing these challenges is the first step towards building responsible and robust systems. And stability is a fundamental quality for any robust ML systems. whether it's handling shifts in data distribution, minor tweaks in hyperparameters, or changes in operational environments, our models must deliver consistent performance. In production, where conditions constantly change, a stable model is one that adapts gracefully and reliably, ensuring that our algorithms do not break down when they are needed the most. Consider the example of financial trading algorithms that excelled during a prolonged bullish market that collapsed when faced with a sudden downturn. These models, having overfitted to a consistent uptrend, failed to adapt to the market stock, resulting in significant financial losses and a loss of investor confidence. This example underlines that ignoring stability can result in catastrophic outcomes, not just technical failures, but real-world damage. So let us discuss the 4 principles of responsible machine learning. There are more if you take a look at different responsible ML frameworks, but we'll discuss 4 of them since they normally exist in every responsible ML guideline. We start with the first principle, ethics. In responsible machine learning, ethics means minimizing harm, ensuring fairness, and respecting people's autonomy. It's not just about building efficient models, it's about creating systems that treat everyone equitably. One key action here is regularly auditing our models for bias. For example, facial recognition technology might struggle with darker skin tones, leading to inaccurate and potential harm. This highlights why diversity in data and fairness checks are critical. Our goal is to make sure our AI system serves everyone fairly. By staying proactive and ethical, we can avoid unintentionally causing harm and ensure justice is at the center of everything we create. Transparency is critical in building trust and accountability in machine learning systems. When decisions come from a black box, it is hard to understand why a model behaves the way it does, which can undermine its acceptance and reliability. To address that, we have tools like SHAP and LIME and a whole bunch of explainable AI that help explain our models and help explain how they make decisions by showing influence or individual features. But transparency goes beyond interpretability tools. It also requires structured communication. This is when model cards come in. For example, Google's model card provide a clear, standardized way to share a model's purpose, performance, and potential limitations. By being transparent, we not only enhance user trust, but also ensure ethical and responsible AI use, aligning with accountability standards. And transparency is not just about tools, it's about creating an open dialogue between AI developers and users. Reliability and stability are essential for any machine learning model to succeed in the real world. First, models need to be tested against diverse datasets and use cases. This helps ensure they are not just performing well in controlled environment, but also in varied real-world scenarios where unexpected challenges might arise. Second, continuous monitoring is key. Data is not static. Changes in data patterns, known as data drift or concept drift, can significantly degrade model performance over time. By tracking these challenges, we can update and adapt models proactively. Finally, stability is about long-term success. Building systems that can adapt to evolving user needs ensures not only their relevance but also their trustworthiness over time. Accountability is the foundation of trust in AI systems. It begins with clearly defining who is responsible for the outcomes of a model, whether it's success or failure. This principle is especially critical in sensitive applications like autonomous vehicles or healthcare, where mistake can have life-altering consequences. For example, who is liable if an autonomous vehicle crashes? These are not just technical questions, but legal and ethical challenges we must address. With the rise of new regulations globally, it is crucial to align AI practices with these frameworks. But accountability doesn't stop at compliance. It also involves proactive monitoring, regular audits, and transparent communication with stakeholders. Only when accountability is baked into every step of the AI lifecycle can we build systems that are reliable, fair, and ultimately trusted by society. The quality of a machine learning model is only as good as the quality of the data we feed into it. This is where the garbage in, garbage out principle becomes relevant. Let's break down the critical steps in data preprocessing, the foundation of any machine learning pipeline. The first one is data cleaning. It involves identifying and fixing inconsistencies, errors, or duplicates. Imagine a data set for customer analytics where phone numbers are in different formats or have typos. If these aren't addressed, it could affect downstream predictions. Similarly, rows with missing keys field, like income or age, might require removal or imputation, and cleaning ensures we start with reliable data. Validation checks during data validation ensures logical consistency and data integrity. For instance, in a medical data set, imagine encountering negative values for age or impossible combinations like male patients being listed as pregnant. These errors must be corrected before training, as they could confuse the model and lead to unstable predictions. And data balancing is crucial, especially when datasets are imbalanced. For example, fraud detection datasets where fraudulent transactions make up less than 1% of the total data. If left unaddressed, the model might disproportionately favor the majority class, effectively ignoring rare but critical cases. Techniques like oversampling, undersampling, or synthetic minority oversampling, SMOD, can help here create a more equitable dataset for training. Or this problem can be solved with a proper cross-validation scheme that saves this disproportion. Ethical data handling. A key ethical consideration is how we handle edge cases and minority data points. Discarding such data because it's sparse or difficult to process can perpetuate biases and lead to unfair predictions. Instead, we must preserve and appropriately weight this data to ensure fairness. For example, retaining data on underrepresented groups in hiring dataset ensures the model doesn't unintentionally exclude qualified candidates from these groups. And by prioritizing data quality, validation, and balancing, while handling data ethically, we set the stage for robust, fair, and responsible machine learning models. Outliers and anomaly detection is another critical step in responsible machine learning, ensuring that our models are robust without losing valuable information. And let us break down some techniques. So it's like isolation forest that identifies anomalies by isolating them in a tree-based structure, or density-based spatial clustering, or DB-scan. It clusters data points based on density and flags sparse regions as anomalies. Or we can use robust statistical methods that rely on statistical measures. But we should approach all this with caution. While these techniques are powerful, we must process them carefully. Outliers might represent critical data points from minority or vulnerable groups. Blindly removing such anomalies could reinforce bias. For example, in a hiring dataset, an outlier might be a highly qualified candidate from an underrepresented group, and preserving such data ensures fairness. So, proper outlier handling improves fairness by retaining diverse data and avoids overfitting by addressing genuine anomalies. Additionally, anomaly detection contributes to the stability of models by making them resilient to noisy or unexpected data points. Interpretability is at the heart of responsible machine learning. It answers the crucial question, why did the model make this decision? Let's take a look at some core interpretability methods. Shapely additive explanations. They quantify how much each feature contributes to a prediction based on cooperative game theory. For instance, in a bank's loan approval system, SHAP can identify whether income, credit score, or loan historically played the biggest role in approving or rejecting a loan. LIME, or local interpretable model agnostic explanations, so they build a simpler interpretable model around a single data point to explain why the regional complex model made a specific prediction. It changes the input features and observes how predictions change. Saliency maps are crucial for understanding deep learning models, particularly in image and text domains. They visually highlight which pixels or text fragments the model relied on for its prediction. For example, it can pinpoint areas of a chest X-ray that indicate potential lung diseases. There are two main approaches like model agnostic and model specific, and techniques like SHAP and LIME are model agnostic, which makes them universal across machine learning models. On the other hand, methods like saliency maps are tailored to specific architectures like neural networks. And each approach has its role depending on the model complexity and domain application. So, why interpretability matters? Well, it builds trust. Stakeholders need to understand how decisions are made. It helps detect and fix biases. For example, if a hiring algorithm weights irrelevant features like names or gender, interpretability tools can reveal the bias. And finally, it is useful in debugging. It can help identify unstable or overly sensitive features. In critical domains like healthcare and finance, interpretability isn't optional, it's essential for accountability and safety. Addressing bias is not just a technical challenge, it's an ethical imperative, and by proactively identifying and mitigating bias, we ensure our models are fair, equitable, and aligned with our values. Privacy is not just a technical challenge. When we collect and process user data, we must ensure it is done responsibly and securely. Privacy concerns directly affect user trust, which is crucial for maintaining a good relationship with stakeholders. And why privacy matters? So, data breaches, unauthorized access, or mishandling of sensitive information can erode trust in organizations. For example, users are more likely to engage with services they think are secure. Beyond trust, privacy regulations like GDPR and HIPAA mandate strict data handling practices, making compliance non-negotiable. And let us explore some techniques to provide privacy. So, differential privacy. By adding carefully calibrated noise to datasets, we can ensure individual level data is obfuscated without losing the overall patterns and insights required for analysis. For example, Apple uses differential privacy in their data aggregation methods to enhance user privacy. Another one is federated learning. This innovative approach ensures that raw data stays on the user's device. Only aggregated updates, which are anonymized, are sent back to improve the model. Google has implemented federated learning in Gboard to improve typing predictions while keeping individual inputs private. And regulatory compliance. So government worldwide have created strict regulations to protect user data. Like GDPR mandates data protection practices across the European Union with heavy penalties for non-compliance. CCPA ensures Californian residents have transparency and control over their data. And HIPAA safeguards medical records in the US, ensuring sensitive health information is handled securely. Privacy is more than just meeting legal requirements. It's about creating systems that respect individuals and their data, reinforcing trust and fostering long-term reliability in our solutions. Security in machine learning is not just about ensuring system functionality. It's about anticipating and defending against threats. Let's start with evasion attacks. This involves manipulations in the data, like changing just a few pixels in an image, which can completely fool a classifier. Poisoning attacks, on the other hand, go after the training process itself by corrupting the data used to build the model. To encounter these threats, adversarial training has emerged as a robust defense mechanism. By intentionally introducing adversarial examples during training, we can make models more resilient to similar attacks. Gradient masking is another popular strategy. It reduces the vulnerability to gradient-based attacks by obfuscating how gradients guide adversaries. However, it is critical not to overly depend on this measure as attackers evolve. What's fascinating is the correlation between robust defenses and overall model stability. Systems built to withstand security threats often show better real-world consistency and reliability under diverse conditions. This highlights the importance of integrating security measures into every stage of machine learning development. Let us talk about conformal predictions, a powerful technique for quantifying uncertainty in machine learning. Unlike single-point predictions that can often mislead, conformal predictions provide a range of possible outcomes, accompanied by formal confidence guarantees. For example, instead of predicting a customer's credit score at 720, it might predict a range of 700 to 740 with 95% confidence. This is especially useful in risk-sensitive domains like healthcare, where a wider interval might indicate uncertainty in a patient's diagnosis, prompting further tests, or in finance, where confidence bands on stock prices guides safer investment decisions. By addressing uncertainty, conformal predictions not only make models more interpretable, but also provide greater trust in the outputs. Machine learning or deep learning models are trained on data to obtain the relationships and give predictions on the data. However, this highlights the problem that correlation does not imply causation. For example, we can try to compare per capita consumption of margarine with a diverse rate in Maine. As we see in the image, both show a high correlation. A model in this case could extract the correlation of both variables, but we have a spurious correlation. Since the model does not understand the causes behind the relationships between the data, it makes it necessary for us to understand the question of why these relationships exist. And it is here that little-known science is born, although it is also increasingly on the rise, and this is the causal inference. Causal ML enables us to move beyond surface-level correlations to uncover the true cause and effect relationships. This is critical in scenarios where interventions must yield predictable outcomes. For instance, A/B testing is a fundamental technique for randomized experiments, But when randomization isn't feasible, methods like instrumental variables provide solutions. Additionally, difference in differences, DID, helps us evaluate causal effects by analyzing trends over time. Real-world applications are vast. Think about personalized marketing campaigns, evaluating public policy changes, or optimizing healthcare outcomes. Models rooted in causality are naturally more robust because they rely on fundamental relationships rather than just patterns, making them stable and reliable in the face of shifting conditions. This is especially valuable in high-stakes fields like finance and healthcare. Let us explore tools and resources for implementing responsible AI effectively. Microsoft Responsible AI Toolbox provides a comprehensive suite of tools for error analysis to identify patterns in model errors, and learn to assess and mitigate fairness-related issues. InterpretML for model interpretability, DICE or counterfactual analysis to explore what-if scenarios, EconML for causal analysis, and data balance. It features to help users understand their data distributions. Also, what is important is the HACS playbook, Human AI Interactions, is a tool for proactively and systematically explore common human AI interactions failures. The playbook enumerates failures relevant to your AI product scenarios, so you can design ways for your end users to recover efficiently. The playbook also provides practical guidance and examples on how to simulate system behavior for early user testing. For predictive intervals, MAPI, Model Agnostic Predictions Interval Estimator, is an excellent resource. Alibi specializes in model inspection and interpretation, enabling users to probe deeper into model behavior. As for the deep learning, Torch CP serves as a toolbox for conformal predictions research, offering a robust framework to estimate uncertainty. You can explore the Conformal Prediction book and course, or for causal analysis, consider Causality for Machine Learning article, or Causal Machine Learning book. These tools and resources provide a strong foundation for integrating fairness, interpretability, and causal reasoning into your machine learning workflows. Use them as building blocks to ensure your AI systems are robust, transparent, and ethical. Responsible AI in organizations is about building a culture where everybody, from engineers to executives, take ownership of AI ethics. It's not just a task for the tech team, it's a shared responsibility. Collaboration is a key. Engineers must work hand in hand with ethicists, legal experts, and designers to address ethical concerns effectively. Lastly, responsible AI doesn't stop at deployment. Continuous monitoring is essential to ensure fairness, safety, and adaptability in the face of changing conditions. By adopting these practices, organizations can lead with accountability and trust in their AI systems. And let us explore some of the leading companies implement responsible AI. Microsoft follows a responsible AI standard to ensure fairness, transparency, and reliability in their AI systems, making tools like AI-powered features helpful and non-harmful. Google uses AI principles, focusing on socially beneficial AI applications, such as disease detection, while actively avoiding misuse, like unethical usage of the ML. Meta takes a privacy-centric approach, building fair AI systems that enhance user experience while safeguarding user data. And finally, Amazon emphasizes safety and reliability by testing AI technologies like Alexa or like warehouse robots to ensure they perform accurately and responsibly. And these examples show the diverse strategies companies adopt to integrate responsible AI into their operations. You can take a look at the Responsible AI standard by Microsoft via this link. Those are the core principles by Microsoft, it's fairness, reliability and safety, privacy and security, inclusiveness, transparency and accountability. And those are similar to the ones that we discussed today. Let's talk about how you can apply the principles. First, always work as a team. Do not try to solve AI challenges in isolation. Collaborating with diverse teammates helps bring different perspectives, from technical expertise to ethical insights. And second, ask critical ethical questions at every step. Who will this impact? Is it fair? Could it harm someone? These questions will guide you toward building more responsible systems. And lastly, make sure to use what you know. Apply lessons like fairness metrics or model testing to validate your AI prototypes. These small steps will make a big difference in ensuring your AI solutions are ethical, reliable, and impactful. Achieving stability and responsibility in machine learning requires a dynamic approach. And first, regular data validation is critical for detecting shifts in distribution or underlying patterns. Concept drift can undermine model performance. Robust training methods like incorporating adversarial examples or simulating extreme scenarios help fortify our models against unforeseen challenges. But we don't stop there. Continuous monitoring systems equipped with automated alerts keep an eye on fairness, bias, and performance. Most importantly, these alerts must lead to actionable steps for immediate mitigation of detected issues. Together, these practices create a cycle of trust and resilience in ML applications. As we look to the future, responsible ML will face both incredible opportunities and serious challenges. The rise of generative AI and large language models amplifies interpretability issues and ethical concerns. Simultaneously, real-time drift adaptation will grow in importance as we deal with constantly changing data environments. Emerging legal frameworks, such as AI Act in the European Union, will set higher standards for fairness and accountability, compelling us to stay ahead of compliance. Lastly, the future lies in effective human-AI collaboration, where we design systems that empower human decision-making while staying strict on ethical principles. The road ahead is as exciting as it is demanding. Let us have some key takeaways since we're moving to the end of this lecture. Let us summarize. First, the 4 pillars of responsible machine learning are ethics, transparency, reliability, and accountability, must guide every stage of AI development. Equally important is addressing bias and ensuring fairness using techniques like fairness metrics, adversarial debiasing, and data balancing. Interpretability empowers stakeholders to trust and understand our models. Robustness and stability are non-negotiable in real-world applications, requiring proactive monitoring for challenges like data drift and adversarial threats. At the organizational level, fostering a culture of responsibility is crucial. Cross-disciplinary collaboration and strong MLOps practices are key enablers. And lastly, as AI evolves, we must prepare for challenges from large models, tighter regulations, and adaptive systems to future-proof our innovations. Together, these elements create a roadmap for building responsible and impactful AI systems. Today, we have explored a world where technology meets ethics, innovation requires accountability, and AI becomes a tool for positive change. We have learned about the importance of ethics, transparency, reliability, and accountability, the 4 pillars of responsible AI. We have discussed techniques to mitigate bias, ensure fairness, and build trust through interpretability and explainability. But most importantly, remember this: you are the architects of the future. The decisions you make when building AI systems will shape industries, communities, and even lives. And take responsibility in designing systems that not only work, but work responsibly, systems that bring value without harm, and innovations that empower everyone and not just a few. And as you move forward, ask yourself, are my AI models fair and inclusive? Do they remain transparent and robust under real-world challenges? Am I contributing to a world where technology is a force for good? Now you have the tools, knowledge, and mindset to make a real impact. Go out there and be the leaders who prioritize responsibility, ethics, and trust in every AI solutions you create. And the future is not just waiting, it is yours to shape. Let us build it together and responsibly. Thank you, and I wish you all the best on your journey.